online. So my name is Daniel Marbach, and you're here in track 1, the evolutionary history of RabbitMQ NET Client towards concurrency. So I work for a company called Particular Software, and we are the makers of Enservice Bus. And as part of my job at Particular, but also in my free time, I worked a lot on the RabbitMQ .NET client. So for multiple years, since the version 4.1, I have been contributing to the RabbitMQ .NET client and helped to gradually evolve the client into more modern and concurrency-enabled library, together with the VMware team. At that time, they were still called Pivotal, but now they're owned by VMware, as well as other stellar community members have helped me together to actually evolve the client. So in this talk, I will teach you, I think, very valuable lessons about what I have learned personally about async and concurrency, and how you also can evolve your own business code bases or your infrastructure, frameworks and libraries into more modern concurrency-enabled paradigms. So I guess many of these lessons can be translated into your daily work as well. And of course, on top of that, you will get deep knowledge about async, the TPL, the task parallel library. And I also will recap throughout this talk some fundamentals of asynchronous and concurrent programming. So the goals of this talk is that I can't assume that everybody's familiar with the RabbitMQ broker and the client. So we'll briefly recap that so that everyone is on the same baseline. And then I will go through why the client makes it particularly hard to actually achieve concurrency with the existing client. And then I will walk you through the experience that I had together with the VMware team and the community members to evolve gradually the client, the .NET client, towards a more modern concurrency-enabled client. So that you get a brief overview what I will be talking about, I quickly tell you the high-level things that I'm going to talk about. So first of all, what we did there, the process was the following. We tried to understand the synchronous path in the RabbitMQ client, and then we tried to optimize the synchronous path, and then we introduced a redundant asynchronous code path into the RabbitMQ client, and then and that is basically already the things that were the most important stuff. So in this talk, what I'm going to do, I figured like, okay, instead of going through thousands of boring slides and make you all fall asleep, because you're probably already on low sugar, because it's almost lunchtime, I figured why not go through some demos and real code in the IDE. So I'll be spending most of my time in the IDE. By the way, should you have any questions, feel free to shoot the questions into the chat of the WebEx. Please do not use Slack right now, because I will not be monitoring Slack, because there is a limit to my brain capacity, how much concurrent things I can do, even though I'm talking about concurrency. But yeah, feel free to shoot things into the channel. Should also be the font size a little bit too small and you want me to zoom in, feel free to shout out as well. I will be watching during the talk and try to anticipate the questions as I can. Okay. So like I said, we will first of all go into what is the client itself. So, and before we do that, I actually want to talk about what is RabbitMQ itself. Well, RabbitMQ is a messaging, an open source message broker, and how VMware puts it, is the most widely deployed open source message broker. So what does it mean? It's basically, it's like a server, it can be clustered, and clients that are producing messages can send messages to the server. They will be durably or non-durably stored depending on the configuration, and they will be reliably or not so reliably depending on the configuration as well, delivered to all the consumers that are waiting on the other side and are also connected to the broker. The RabbitMQ, the broker itself, for historic reasons, it implements the AMQP 091 protocol. The AMQP 091 protocol was later then broken and entirely broken, and it was redeveloped into AMQP 1.0 specification. And it's a completely different protocol, AMQP 1.0. AMQP 1.0 is supported by RabbitMQ, although you have to have a plugin on the broker side to actually enable clients that primarily talk MQP so that they can send and receive messages from the broker. So what we can say today is that the MQP 091 protocol has become de facto the RabbitMQ protocol, and it primarily defines exchanges and bindings and queues and how these things actually interact together. And as far as I know, nobody else in the industry right now implements the MQP 091 protocol. If we are pulling down the RabbitMQ client into our .NET solution, we're going to NuGet to search for the RabbitMQ .NET client. And then what we're getting is the first entry point is the connection factory. Here I'm running Docker, so I have it on localhost. This is port 555672. I'm also telling the connection factory to use background threads for IO so that it has named threads behind the scenes so that I know what's going on. The connection factory itself is the one that connects to the broker and creates connection objects. Connection objects can be created here with create connections. You can give them a name so that you can see what's going on. And connections, they represent long-lived MQP09 objects that then what they do is they, for example, observe the connection between the client and the broker. And if you, for example, lose the connection, the TCP connection there, it does the actual connection recovery. It also maps the frame, the protocol frames that are underneath to the headers and commands and everything else of the underlying protocol. Now, when you have a connection, the most important piece there, and that's the thing that actually enables you to interact with the broker itself, is what they call iModel. Sometimes it's also referred in the documentation to as channels, so that's a little bit confusing. So these two words are basically used together, so model and channel. I'm trying to stick to more to the notion of model, because later on I will be using channel in a different term so that it doesn't get too confusing. Okay, so the model, what it is, it basically represents this MQP09 piece that is a long-lived interaction over the connection with the broker and the broker protocol methods. Applications that are using multiple threads and multiple processes, they actually should be opening more or less, let's say, one channel per thread and one channel per process, and threads should not be sharing the models in between. And so what you have to do is you have to establish basically a clear notion of how you map in your application or server model, how you map your code to the models that you're creating via the connection. Most importantly, it's on the publishing side. So you should never ever mix multi-threaded publishes on the same model. The problem is if you start doing that, what's going to happen is on the protocol level, there will be frame interleaving happening. And then when frame interleaving happens, because you're sharing the model with multiple threads, then things are going wild. So what it means is the broker will not be receiving what you just sent. It will be receiving some binary chunk garbage, essentially. A single connection that you're creating against the broker can have up to a max 100 channels. That's though a setting that can be configured on the server side. But as you can probably imagine, if you have to manage multiple models on your side, it can become quite complex. And on the other hand, what's also possible is the more models you're creating on the same connection, the more the performance and throughput will go down for your client, as well as the more models the server needs to deal with, the more the throughput can go down as well. So you need to carefully balance basically your application's needs in terms of scalability towards the client interaction model that you have with the broker. And then once you have this model, you need to create an eventing basic consumer that you pass in the receive model or the model that you're using. And then on this eventing basic consumer, you have event delegates, and these event delegates will fire whenever there is a message on the broker, and then you can do your code. So here in here, what we can see is we have this consumer received event handler delegate where we're getting these basic delivery event arcs. What we do here is we just print out something. We then do a thread sleep to simulate any kind of work. And then what we do is we call on the receive model, the basic ACK with a delivery tag. For conceptually, the delivery tag, you can imagine this is almost like a GUID. It's basically a unique identifier that identifies your incoming message. And you can then, with that unique identifier, you can then say to the broker, hey, I actually successfully handled this message, or I did not successfully handle this message. Then you're necking the message, and then the broker will redeliver it again to the client or to another competing consumer that is connected on that same queue or exchange, for example, that you're having on your server. And then what we have here is we also have, we can send messages. I'm using a confirms aware model or channel. And what this is basically a reliable way to transfer messages over the broker. What this is going to do is it sends a message to the broker, and then it waits until the broker has actually acknowledged that the message is durably stored on the broker side. And when that happens, the broker then sends over the connection protocol over MQP 091, it sends back to me a message that says, hey, by the way, I actually successfully handled the message with this consumer tag that you just sent me. Why is that important? Well, by default, you don't get these delivery guarantees. So what that means is you might be sending to the broker messages, but then, and the broker says, yep, okay, I got it. Right, but it hasn't really durably stored it. So if the light goes out and your broker is not highly reliable, it might be that the message is gone. So that's why we're using this confirms aware channel to actually send messages. And as you can see here, I'm sending every 450 milliseconds. I'm sending messages to the broker. So let me show you how this demo works. These are the basic client bits. Cleaning up my screen. .NET Run. So now I'm running this sample. As you can see on the left side, we're sending a value. On the right side, it's the current state of the queue on the broker, represented with the letter Q colon. And because we're sending more messages than we're actually receiving, right? Because we can only handle one message at a time, and we're doing thread sleep, the messages will be basically piling up on the broker. Okay, so what we can say is, right, because we're only handling one messages at a time, the more we're sending messages and the more we're increasing the sending speed, things start piling up. And of course, we could say, well, one way of speeding up processing of messages would be if we, for example, horizontally scale out the consumer. So we would be copying basically this process and connect it to the broker. And then we would have many copies of that running that receive messages from the broker. But on the other hand, well, wouldn't it be nice if we could, for example, make sure that we are efficiently using the resources that a single client can actually have? So not just basically scale out, but first of all, we want to scale up, right? So we want to basically introduce concurrency into the client application so that we can receive multiple messages at the same time. Of course, what you can do is normally, for example, we just saw it up here, right? You could create multiple models, but we talked about how that can get complex, especially with the restrictions on the server side. Or you could be creating multiple eventing basic consumers to try to consume multiple messages. But dealing with that code can also get extremely complex. So what have most clients that are using the RabbitMQ client, what have they been doing? Let me show you how you can achieve concurrency. So the basic bits are still the same. We're creating a connection factory and all that stuff. And in order to, when we go into concurrency land, right, one of the most important factors we want to take into account is we want to make sure that we throttle requests at some point, right? Because if you're just going and saying, hey, just give me everything you have on the server. Well, if you just have 3 messages on the server, well, that's not going to have a big impact, right? But let's say if you have a DB connection pool of 100 DB connections that you can currently create, and you have 1,000 messages on the server and you're going without concurrency limitations, the server will deliver you 1,000 messages, right? And then you're trying to spawn up 1,000 concurrent consumers, and they will be overwhelming the DB connection pool and things start timing out. So we want to make sure we limit the concurrency. And we do that by having a semaphore slim, which is going to basically gatekeep things so that things are not running in unbounded concurrency fashion. Then we're going to, again, wire up the received delegate, and then we start kicking off. Now, the problematic part is that the consumer delegate here, it's a regular .NET event handler delegate. So what we return here is void. So now, if you're accustomed to do TPL, task-based programming, you're like, okay, void, kind of evil because, well, how can we actually introduce concurrency? Well, one way is that you start going into custom offloading by using task.run or any of your preferred worker thread pool offloading mechanics that you usually use. Another one is, well, you use async void, right? But as you probably remember from the async best practices, async void is kind of evil. Why is it evil? Well, the thing is, first of all, async void, when you enter the thread that enters the method, will synchronously execute to the point where the first await statement comes that truly yields into an IO completion port. So that means everything here is executed synchronously, and everything that throws up to that path will actually synchronously throw up. So that's fine, right? So for example, if the client bits assume that if an exception is thrown, they're throwing some other event handler delegates, then that will work. But as soon as we have an await statement in an async void code, that will no longer happen, because from the perspective of the caller or the invoker of this event handler, the call is already over and they will continue to do stuff. So now that also means if you're using async void, and even, for example, if you're using task.run, what we would have to do is we have to first copy the buffer that we're getting from the client. Why do we have to copy the buffer? Well, if you don't copy the buffer, it is possible that as soon as we are going into concurrency land, because we return back to the client, but we're still processing the bytes payload that we got from the server, what's going to happen is the client will start collecting the allocated buffers and clean them away. And if we don't copy it, we run into creating garbage because of reused buffers. And then again, we need to acquire the semaphore and to limit the concurrency. But now we have another problem, because regularly what happens if, and we said we want to handle, let me go back up here, we have a concurrency of 4. We want to handle up to a max for 4 messages at the same time. So what happens is here, if the semaphore still has slots available, the clients can enter the semaphore and the semaphore will synchronously complete. So that means when we run through here and the semaphore still has slots available, what's going to happen is that down here, we will be still on the thread that is invoking us. So that means that is the RabbitMQ client driver threads that are doing stuff. So if that happens, we are actually not really concurrently doing anything, because we are still blocking the thread. So we're not unleashing it. So what it means is it cannot pump more messages to the client application at that specific time. So now what we have to do is we basically have to do advanced trickery, like for example this one, and that's just one way of achieving it. When we enter the method, we store the current managed thread ID. And then once we exited the wait async, and if we synchronously completed, we are still on the same managed thread. And if that happens, we force the current thread to go back by doing an await task.yield. Task.yield, if you have never heard of it, it's basically just a very quick way to tell the current thread, hey, go away. It's similar to thread yield, but just for the TPL APIs. And once we have done that, the continuation, which is this part of the code, will be executed. And now we're in a truly 3-threaded environment, and we're not blocking any thread. And especially important, we're no longer blocking the worker thread that is pumping messages to us. But now comes the next problem. I told you at the beginning that from a channel interaction perspective, it is not possible to interleave calls to the broker. So, but since we are here in a three-threaded environment, if we want to do a basic acknowledgement of the message, what we have to do is we have to make sure that these calls here on this line 128 will never actually interleave with each other, because now we have up to 4 things that are going on concurrently. So we need to make sure they're sequentially executed, although in a free-flowing, free-threaded environment. Let me show you how that works. And first of all, we're going to use the task.factory start new. Normally, you should always be using task.run because that's the API that is almost in 99% of the cases the right API to use, except when you want to do advanced trickery like saving allocations, or in our case, saving allocations, as well as making sure we control the task scheduler that is going to execute this method. So what we do is we offload to the worker thread pool. Why do we offload? Well, because the async, as there is no async RabbitMQ client API, right? So we're still doing synchronous IO. And as you probably know, that's not the most efficient way to do IO, but at least with offloading it to the worker thread tool, although it's a costly operation, we can make sure we have proper concurrency enabled. And then what we do as well is we save the state to save allocations here. And then the most important piece, we're passing in the task scheduler from the outside, and we're making sure that nobody can actually attach as a continuation, as a child task to this current task, so that we're not running into weird task dependencies. Okay, but here we need to actually have something that you might have heard of or maybe not. I'm going to explain it to you. So in the .NET framework, there is this concurrent exclusive scheduler pair. What this is, it's basically a task scheduler that has 2 sides. One side of it is, well, do whatever you want to do and concurrently execute and interleave calls. And then there is the exclusive scheduler, and the exclusive scheduler will make sure that anything that is scheduled on that exclusive scheduler will always be sequentially executed in the order where they were added. Well, order is not entirely guaranteed. There's no strict ordering in there, but at least somewhat ordered, and definitely not interleaved, right? So, and with that, by providing this exclusive scheduler down here to the basic ACK signal, to the receive model, all the basic ACKs will never be executed interleaved. And then at the end, we just release the semaphore so that we have enough, so that we can release the semaphore slot so that we can concurrently process messages. Well, okay, let me show you how that looks like. Let's go back. Let's go to the concurrency example. Let me clear the screen right now so that you can better see it. I'm running now this demo. And as you can see here, we're getting 4 messages, and we had to 4 times yield at the beginning because we're still on the synchronous path of the semaphore. And now, with all the trickery in place, we can concurrently handle up to 4 messages. Things are still piling up on the server because we are still sending faster than we can more or less receive. But we have at least achieved some kind of concurrency. And now that we have concurrency, I also want to briefly show you why we have to buffer copy. So if I don't buffer copy, and if I remove here the to array, where I force a copy of the memory, and then I'm passing the span to getString, so that's the current buffer, what's going to happen is the following. Let me show you the demo again. Exactly same code. Now I'm executing it. The first ones are working, and now we're getting hearts and smileys and everything. While this looks pretty cool in the demo, right? Because who doesn't love to see hearts on screen? I mean, in your production system, that would be very terrible because you're probably not going to send hearts around because you're probably going to send business garbage around that nobody can receive, right? And you don't want to deal with that. Okay, so that was the demo of showing how we actually need to buffer copy. So let me do a brief recap of what we have just seen here. Even though RabbitMQ is IO bound, so it interacts with TCP sockets and the underlying MQP protocol and everything like that, it's mostly purely sync, right? We saw that the event handlers, they return void. And in order to bring true asynchronicity, where we can actually work with tasks to make sure we're not blocking any thread, from the consumer perspective, we have to go through a lot of hassle, and it requires a lot of advanced trickery to get things working. So really the question at the time was, well, why does someone that is working with the RabbitMQ driver, why do they have to deal with all this stuff, with all this crazy stuff? And how could we achieve better concurrency and asynchronicity to basically support a first-class concurrency on the client side? Well, we started initiating, and primarily I started initiating the conversation with the VMware team at that time, and we talked to them and said, well, at that time, for them, it wasn't really an option to basically go async all the way and touching all the model methods. I mean, that's clear, right? It's also, if you have an existing application that has hundreds of thousands of lines of code, and you're going to your boss and saying, hey, boss, I'm going into the dark mode for the next 6 months, and I'm going to refactor everything and redesign everything without delivering any business valuable code, you're probably not going to succeed in that conversation with your boss. I'm not sure if you're still in business, right? If you're the only one, if you're your boss yourself and you haven't actually delivered any meaningful business features within 6 months, right? And we had to do the same there. So we had to try to find a way how we can gradually evolve. And the decision at that time was, well, we start from the receiver side. So the high level idea is that we need to find the best entry point into the client to introduce asynchronicity without breaking all the consumers that are currently using the RabbitMQ client. Because like I said, in the abstract, there are more than 30 million downloads of the NuGets worldwide, right? There are quite a few people are using this client. And once we have an asynchronous path in there, we want to be able to continuously and gradually evolve the client to introduce async support. And before we did that, we had to understand the synchronous path completely. And let me walk you through that scenario. So the first step that I usually do is when I go to an existing code base where I have to introduce asynchronicity is I have to fully understand what's going on the synchronous path. So let's have a look at the consumer work service. That is the consumer work service that we had at the time. I'm showing you a lot of code. I'm not going to walk through everything. And it's also not really important that you understand every bit and piece that I'm showing you right now. It's just, as you can see here, the client has the worker service, and that's the service that is responsible to pump messages towards your code. Has action delegates internally that will get a lot of closure allocation, so a lot of memory pressure, Gen 0 memory pressure, a lot of custom scheduling on task scheduler for legacy purposes, and so on and so forth. So what I did there was I ran a test to actually see how does the current code behave. And surprisingly, what we found out is that it didn't behave as you would expect. So at that time, I've used multiple machines to actually test it. We had like the Core Duo Intel processor. As you can see, with one consumer, we're able to pipe through 6,900 roughly messages a second. With 32 consumer, we get 7,600 and some more. And with the Sandy Bridge CPU, we got, with 32 consumers, we got a nice performance improvement up to 11,000 messages a second. And now comes the funny part. And by the way, yes, I'm that old. No, well, in CPU years, I'm probably not that old because CPUs evolve quite quickly, right? But yes, we were using Core Duo and Sandy Bridge and stuff like that. And the most modern that we had was the Skylake processor. And there was a comment in the chat about the concurrency example, especially. I will try to deal with the question a little bit later, where it nicely fits into the conversation flow. But here, as we're using the most modern was Skylake, and as you can see, well, you just bought a precious new CPU, and you're like, yes, I'm going to test the RabbitMQ client, and it must be faster. Surely it's going to be faster, right? And you're fully excited. You run your benchmarks, and you see like, oh no, it's actually not. What a terrible day, right? We're only getting 2,200 messages a second. So what we can say is the more modern the CPU becomes, more or less, the more gradually the performance of the client went down. And that's a pretty terrible situation to be in. So the reason why this was this so-called batching work pool that is used internally. So the batching work pool is used by the worker service, and it uses, as you can see here, a global lock per batching work pool. And what we can say is, what you could observe at that time, if you use the profiler of your choice, you could actually observe that the client, the more modern the CPU is, the more lock contentions you're getting, because multiple concurrent operations are trying to acquire the lock and reacquire the lock, and will go into the monitoring and can't exit until another one is released, and multiple will try to again to acquire the lock. So the lock contention was extremely high. So what you have to look for if you are going into the concurrency land is, first of all, look at your synchronous path, like we did in RabbitMQ, and try to see if there are locks in there. Well, first of all, we said, yes, lock contention is bad. Well, because it actually pulls down orders of magnitude in throughput on your code, because multiple threads will be waiting and have to basically try to reacquire the locks. But what's even worse is if we want to introduce into a code path asynchronicity, so the async await keywords and tasks, we can never do that inside a lock statement. The compiler is going to tell you, you are crazy. Nobody does that. Why is that not possible? Well, maybe you remember from the fundamentals of C# and locking, the thread that actually enters the lock, acquires the lock, is the thread that has to release the lock. So, of course, when you have an await statement where we are actually in a free-threaded environment, it cannot be guaranteed that with your try finally block, in the final block, when the lock is released, so basically that is on this line, that is still the same thread that acquired the lock, right? So you have to also get rid of locks when you want to truly use async await. And now I'm going to get to the question. There's one question: would one use this approach to throttling when you have multiple queues being read on the channel? I'm trying to see when this should be ideal versus setting the prefetch count to say 4 in your example. Okay, yes. So let me quickly go back to concurrency. You could definitely use the semaphore slim to also throttle requests from multiple queues. That is possible. The prefetch count, I have not talked about this. This is this part here. What the prefetch count basically just does, it just says, well, go and fetch in one network call up to the number of messages from the broker and buffer them locally, and then dispatch those. So what we're doing with a prefetch, we're only making sure that we don't have to continuously reach out to the broker to get more messages, right? But that's really more or less independent, a setting that is independent from the concurrency semantics that we have on the client side, right? The thing that we can do is we can optimize for more fetching and for less latency in the interaction with the broker from pulling in the messages. I would still use a semaphore slim that controls the concurrency that I want to have in my application code. Hopefully that answers that question. Okay, so what we did is, well, we try to get rid of these locks, because even, like I said, when you have locks and lock problems, not even async is going to help you at all, right? So we need to first optimize the sync path. So we introduced a new work pool, and let me scroll up a little bit. I'm sorry. So here we have the consumer work service that was revamped. It uses a concurrent dictionary internally to handle multiple work pools. But the most important part is not this one. Of course, we're already getting a lot of nice benefits just by handling multiple models and worker pools. But the best thing is here in the worker pool. So we're using now a concurrent queue with action delegates, still some closure allocations, an auto reset event to make sure that we're only actually trying to get stuff from that concurrent queue when things are actually ready. And then when we're starting either a custom thread on the background, or using the TPL. With TPL, we cannot name threads, right? So that's not possible. We start a background thread if we're not using .NET Core, so that we have a nice benefit of having named threads. I didn't make that choice. That was at the time already there, so we just made sure that's still supported. And then what we do is when we enqueue a new action, we just throw it into the concurrent queue, and then we set the message arrived auto reset event to a set state. What that means is the loop that is running in the background, most of the time, if there is nothing to consume, it will be sitting here on the wait one, and it will wait until the wait time is over or someone sets the auto reset event. And then once we have something and we're not canceled, we're trying to, as efficiently as we can, getting stuff from the concurrent queue, try to dequeue the actions, and then we execute the actions there. And that's the basic gist, just the first iteration of making the sync code better. And what we got here is already this really nice improvements. By the way, I'm showing you the benchmark results that we did from the high-level perspective from nService Bus using the RabbitMQ client, the newer versions of it. So the actual raw numbers, by just using the client, might be even different. But here, when we let's focus on the right side here. The receive throughput improvements on our side, just by using async await, was 1.69. Once we removed the lock contentions, we got up to 6.66 times more receive throughput, just by introducing this smarter consumer work service that doesn't have the same lock contention problems. So if we go back here, right, onto this example where we looked at the Skylake processor, so we can actually say that on any CPU we're getting up to 6.6 times more, 6 times more receive throughput, and that scales very well also with even more modern CPUs. So now we're at the stage where we can say, at least from a synchronous path perspective, buying new CPUs actually makes sense, right? Previously, it wasn't a good investment with the RabbitMQ client. Okay, so the key takeaways that I want to give you here, if you can go into your synchronous path and remove the locks, that's a very liberating procedure for your code. And you get orders of magnitudes of improvement just by doing that. And we haven't even talked about async, right? So now we're going into the meat. Now we're going into the async stuff. Okay, so like I said, because RabbitMQ had a large user base, and we couldn't just break everything, we had to gradually change things. So one way, like most software problems get solved, right, is to hack stuff into your existing code. I'm sorry, but that's how things sometimes work, right? So we introduced a new interface. It was called Async Connection Factory, where you have dispatch consumer async. Once you have that enabled, what's going to happen is the connection will basically do an internal type safe cast, and will check, well, is the dispatch consumer async flag set to true? And once that is in there, it hooks in a new async consumer work service that is geared towards the async path only, right? So that is how we introduced a redundant async path. And then, well, from a client perspective, what you have to do now is you can no longer use the eventing basic consumer. You basically use the async variant. So there is the async eventing basic consumer, or the async default basic consumer. And the most important part here is they're using this async event handler, which is now a delegate that no longer returns void, and now returns a task, right? So the requirement is, once you set the flag on this dispatch consumer async to true, you have to use the other worker service, and the client will tell you, unfortunately, by throwing a runtime exception. That was the trade-off we had to make in order to not break everyone. Okay, and the consumer work service, a bunch of improvements, like for example, better caching things, stuff. But the most important part is here. So at that time, we were still on the .NET 4.5 framework. So we had to do a few advanced trickeries to make sure everything properly works. So we use the concurrent queue, still action, and then we have a cancellation token to properly support cancellation. And then when we enqueue a new action, what you do is we use a task completion source. A task completion source is just a mechanism of basically have a task where you control the state of the task, you control the outcome. And because we were using the .NET 4.5, we had to use this nasty trickery to basically, depending whether you are on the .NET framework or not, that has a specific version, we had to basically grab with reflection into the internals of the APIs and then flip an internal flag to make sure we always asynchronously complete the task completion source. Why is that important? By default, if you're below .NET 4.6, the task completion source will always, the task that is represented there will always complete on the thread that actually did the try set result. And as you can imagine, that would be very evil, because if the client enqueues a dispatch operation of a message and then it sets try set result, the continuation of the loop, which is what happens when here the task completion source completes, would be executed on the thread that did that. So that means the while loop that we have down here would be executed on that thread, and then we would be blocking the one that gives us the messages, which might be some underlying thread that observes the TCP frames and everything. That would be not a good approach. So then we're waiting here as in contrast to the synchronous version, we're not blocking any thread, right? Because it's async. Once we're getting out, we're resetting the task completion source. There might be races on that field, but this turned out to be a non-issue due to the async fencing semantics and everything. So that worked extremely well. And then once we are down here, once we know something is in there, again, we're trying to dequeue everything that we have, and then execute these action delegates. Okay, so the key takeaways that you have to think about here is that, and that was the consumer work service, and then the async consumer work service is exactly the same, except that here what we're doing is we use exactly the same technique. We do a try set result and we await the task. But now, as you can see here, is when we take the stuff, we're no longer getting actually action delegates. We're getting something that returns a task, and then we just await and execute. And then we're no longer blocking, even when we're executing the async consumer, the async consumers that are attached to this worker service. And by doing so, we free up all the threads that are in place, and we can achieve a very high IO saturation. And freeing up the threads is crucial for modern concurrency-enabled libraries. And the task-based APIs, they are the key to achieve this high IO saturations or value task, even if you're using even more modern approaches. And there is really no way how you can avoid it. And of course, we were quite lucky because we were able to basically bring in over this consumer and async consumer work service redundant code path for client took in. So that was great. But maybe in your business code, that might not always be such a clear cut, right? But still, if you use the same techniques that we learned so far, basically looking for locks, starting to optimize the sync path, then trying to find an IO bound path where you plug in a redundant async path like we just did, you might be able to get a lot of additional gains without having to rework everything that you have in place. So once we did that, the next client version was that we did some cleanups because we bumped the .NET framework support. So we were able to just remove the hex, the task completion source factory. We did some other cleanups as well. So nothing really fancy, but the core of the logic is still the same. One thing that came up, because there was a lot of time passing, was someone from the community asked, well, why are you using a task completion source here? Wouldn't it be much more efficient to actually have a semaphore in place that makes sure things are waiting here? So basically this semantics, we have a semaphore that we release when someone calls enqueue instead of a try set result. And then we do an await semaphore wait async here until we're canceled and then iterate again. Well, that was a very interesting question, and we was like, okay, well, if you can get rid of this complexity with the task completion source, why not? Right? So we then did some performance benchmarks around this. And surprisingly, what we found out, even though the semaphore slim would potentially be the more intention revealing design or the more intuitive way to achieve this, was that what we could see is the task completion source is actually orders of magnitude faster. So the baseline is here, the task completion source. And as you can see is, for example, semaphore slim with a lot of inserts and elements that we're processing. We're getting, we're up to 10 times faster, up to 10 times faster with the task completion source in comparison to the semaphore slim. And of course, here on this side, if you pay attention, you see that Gen 0 garbage is slightly higher with the task completion source approach because we have to replace the field whenever we are going to loop, right? So that is a bit more problematic, but in this specific case, it was actually okay to have a bit more Gen 0 garbage because we wanted to make sure on the enqueue path where the client actually throws in work, we're as fast as we can. That was the thing that we're measuring. So we're making the necessary performance trade-offs. So that means the task completion source was still the most efficient way to do it, and we rolled back those changes. So the key takeaway is, even if you're going from sync, optimized sync to async, measure your assumptions, because your assumptions might not always be true, or your things might even be invalidated. Performance things that you introduce at a certain point in time, if you do not capture these performance metrics in your code, someone else, or maybe even you, because you forgot, right? You have more gray hair and they're coming back and you don't remember all the details, and now you change the code and suddenly things are getting slower. And now with the introduction of the major version 6 of the client, we did a more cleanup. So we were aware that there is this system threading channel that came with the .NET framework. It's also, if you're supporting .NET framework previous versions and you're not running on .NET Core, you can actually pull in a NuGet package that represents the system threading channel. And we started rewriting the async consumer work service to use the system threading channel APIs. And we were able to do that, right? Because we're doing a major version. We are SEMVAR compliant now. You can pull in another additional library because you know you're upgrading from a previous major to a new major version. So now what we're doing is we're creating internally an unbounded channel that allows us to store as many things as we want without blocking. There is guaranteed to be a single reader. We tell it so that it can optimize internally its data structure. There are multiple writers, potentially multiple concurrent writers, and this is also a crucial piece. We need to tell it we cannot allow synchronous continuation, and the example is the same. We cannot allow that the one that enqueues something to the system threading channel is also the thread that actually is going to execute stuff, because that would be not good for the performance. And then when we enqueue, we just use the channel write or try write, and the loop has become tremendously simple. We're just waiting here until the channel tells us, hey, there is actually something to read. And once we have it, we read as much as we can as before. And then we did some further optimizations. So we execute the worker, and many client applications started using the async consumer, the async eventing basic consumer, but sometimes returned task completed. And in such a case, if the task is already completed, we can actually optimize by checking if it's completed. And then we don't need to go into the a bit more expensive allocation heavy path where we use the async state machine. And that's a further optimization. Of course, every time, because there could be something happening here, even if we synchronously complete it, we then need to do get away to get result to actually materialize any exceptions that could have happened so that we are still compliant with the previous behavior of the code. And then we asked ourselves an interesting question. So, well, now we introduce system threading channel. How does this, from a performance perspective, behave towards the task completion source? And I was at that time, I was like, yeah, sure, a library from Microsoft, it must be faster, right? Again, I told you, measure, 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 right? Because your assumptions might not be true. So I did that, ran through benchmarking using benchmark.net. And what's interesting, as you can see here, is we are actually, the task completion source is faster, up to 2.8 times faster than system threading channel. But, I have to say but, first of all, for every benchmark result that you're seeing, you also have to understand the context in which the benchmark was done. And in this context, I only checked the NQ path. So on the NQ path, I'm actually faster using the task completion source. But then, on the other hand, if you would basically check everything from top to bottom, from NQ, also from receive, I am not showing you these results, but then system threading channel is much faster. And what's also important, as you can see here, now things are getting quite interesting, because by using system threading channel, while we might be slightly slower, but not very terribly slower, on the NQ path, we're actually less allocation heavy because we're not using task completion source, and system threading channel doesn't produce any Gen 0 garbage anymore. So that's very nice, right? So yes, it's not just because a performance benchmark told you something is slower than something else. It doesn't mean you have to backtrack and throw out everything in your code, right? You have to understand the context you're operating in. You have to compare and contrast the things and then make the best decision. And on top of that, what's also really crucial is, I think, any code that you can replace, that any custom code that you wrote, or let's say I wrote, I know that I'm a terrible developer and I make a lot of mistakes, right? So any custom code that I can replace, that I wrote, that I can replace with a base class library that comes from Microsoft, that is going to be battle tested, is going to be developed by a lot of runtime engineers, is battle tested by thousands and thousands of people worldwide, is worth replacing by something that comes from Microsoft, right? So not always the fastest solution is the best solutions. All factors have to be taken into account. And in the latest iteration of the client, which is the 6.2 version, it's the current released version, I introduced the notion of concurrency. So what you can do now is, scrolling up quickly, excuse me, you can pass in to the library. You can say, hey, I want a concurrency of 4. And what it does then internally, it then basically, depending on the concurrency level, it either spins up a loop that just does a single execution, sequential execution, or it spins up a dedicated concurrency loop that then operates in a different way and makes different assumptions about how your code is going to behave. Let's have a quick look how it looks like. This is the concurrency loop. Everything else, by the way, I'm not showing right now because it's exactly the same. So again, we're using system threading channel. We're still on there. Then we do a try read. Then we just check whether we have quickly synchronously check in order to not allocate the state machine. If the semaphore still has slots available, if not, we then wait here. And then we just kick off the handle concurrent. And what handle concurrent does, exactly the same as it did before, but now it's basically offloaded, right? So we execute, we do the same checks, we materialize the exceptions. And the most important piece of the puzzle is we do then a limiter release. So we make sure that the acquired semaphore slots are then released again. And now, how does this look like if you use the newest incarnation of the RabbitMQ client? Well, super cool, I think. You can now say dispatch consumers async, you set that to true. You say consumer dispatch concurrency, you set it to the number you want, right? And then you start going. You have this async eventing basic consumer that I've already showed you. And now you just attach the delegate that can return a task. You do proper async await, no advanced trickery, nothing. And you're getting dispatch concurrently this method. And as you can see here, on top of that, we have done further optimizations in the client. So there is no longer a need for passing an exclusive concurrent scheduler pair. Because underneath, because we already have a dependency on system threading channels, for the protocol interactions, the client also uses system threading channels to making sure that there is never an interleave happening on the underlying protocol level. So we can get rid of that. We still, if we want to offload, we still need to use Task Factory Start New because we are not yet fully async enabled. We're still doing synchronous IO on some of the model interaction methods, unfortunately, but it's already much, much better. And let's do a quick demo here. .NET Run. And now, as you can see, we're running, and we're concurrently fetching. Things are not piling up. And as you probably saw, because we can directly use the span here, there is no more buffer copying anymore. So we're like concurrent, highly efficient, and we don't need to waste memory anymore. And the client is also much faster. What does the future hold? Well, the future will hold that with the version 7 and 8, we will get all asynchronous operations on the model. So it will be truly top to bottom async all the way. And there will be more and more allocation reductions on the client to make this an extremely fast .NET client. And let me do a brief recap of what I've just told you. So what you can learn here from this talk is that if you go into your code and find the outbound paths in your application code, in your business code, in your libraries that you maintain, and if you know where IO is going through and you're doing synchronous IO, make sure that you analyze this code for lock contentions and making sure that you're getting rid of lock. That's the first preparation step you want to do. And then if possible, in order to not break everything and in order to not have months of work for not much added value, introduce a redundant code path that goes async all the way. And then from there, you can start gradually extending asynchronicity and concurrency on the IO-bound paths. Important, never block threads, right? Blocking threads is evil, and it's not modern concurrency practices. And then only custom offload where really necessary. Like we saw, because RabbitMQ client interaction is still doing synchronous IO, we still have to a little bit of offload. Of course, we want to avoid this, but this will come in the version 7 and or 8 of the client. And then if you're on .NET 5, you can also start thinking about returning valid task instead of task to actually benefit from buffer pooling, from the valid task pooling underneath. And of course, whenever you can, the code that you don't write yourself, although you're probably much better developers than I am, I encourage you to replace the things that you have in place when you can with reliable, battle-tested BCL components. So like we did with system threading channels. And of course, as a last message of this talk, if you can, contribute back to open source that you use in your company. And because then you can, like me, and some of my other community colleagues, you can make the libraries that you use better and better, and those benefits will come back to you. Thank you very much for attending this talk and listening to me. If you want to see the slides, the demos, the code and everything, it's on github.com/DanielMarbach/async RabbitMQ. If you're interested to see how Answer Response uses RabbitMQ, go to docs.particular.net/transports/RabbitMQ. And yeah, if you have any more questions, I think I can potentially take one question here, but I will also share a WebEx link in the Slack channel, Track1 Slack channel, where you can hop on a call with me and discuss whatever you have on your mind.